Hi folks, welcome back for some more trig equations. As a special kind of meta game on these videos, you can guess what kind of room I'm in based on the reverb. Okay, here we go. We're looking at quadratic trig equations, so we get to combine two of our favorite things, quadratic equations and trig equations. So in this first one, we've got sine squared x plus sine x equals 1. So clearly a quadratic because there's a squared on it. And when we have quadratic equations, typically, unless we're going to use even if we are going to use the formula, we make one side 0. If possible, we factor, and then we solve the elementary equations. Okay, so let's imagine that I had something like this, 2y squared plus y, and I'm going to move that 1 over. So I'll do this for the sine equation as well. Move that 1 over. That's a complicated equation. Let's do it just with y, something like this. You could factor this. So you could say, okay, what's going to multiply to give me 2y, that 2y squared rather, that would be 2y and y. And then I'll have to put a 1 in one of these and a negative 1 in the other. And if you have issues with factoring, I'll put a link to a video down below. Typically, it's the long trinomials that cause people problems. You can do them by decomposition, or I just did mine by guess and check. Okay, once we have that, then what you get is little elementary equations to solve. And in this case, those equations are pretty easy. It would be 2y equals 1, gives us y equals a half. And y equals negative 1 for the other one. There are two solutions. You could also have gotten it with quadratic formula. So what's similar and different between the equation that we have over here? Well, number one, we've got some trig involved. But aside from that, it's really the same quadratic. And when you have a quadratic trig equation, I recommend that you rewrite the equation just without the trig stuff. It's 2 times something squared plus that same something minus 1 equals 0. If we know that with the y's it factors this way, then with the sines, it must be really similar. It must just be 2 sine x minus 1 times sine x plus 1. Now, if I FOILed that out, I really would get 2 sine squared x. I'd get plus 2 sine x minus sine x, so that's plus sine x. And I'd get a minus 1 if I FOIL it out. I'll have to get rid of all those arrows, because what's the next step? We've factored it, so we're going to have elementary equations. 2 sine x minus 1 equals 0, and sine x plus 1 equals 0. It's going to be double the work. These are two trig equations that need to be solved, but it's not double the difficulty. Okay? Each one you can deal with on its own, so I can move that 1 over. I can divide by 2. Okay, there's an equation to solve. And for the other one, I'd just move the 1 over. Sine x equals negative 1. So at this point, on this first one, I'm going to have to find a reference angle. Probably need my unit quarter circle. There's going to be a point right here, root 3 over 2.5 at 30 degrees. Okay, and we are doing this in degrees. So the reference angle is going to be 30. Sine is positive, so I could be in either of the first quadrants. There's no funny business with either the angle's still just x, or with the domain. So a lot of the things that we had to deal with in the last video with weird domains and changes to the period are not here. This is fairly straightforward for this part of the equation. So we're going to have x could be 30 degrees, or we could be talking about this one here, which would be 180 minus 30. Okay. So x could be 150. If we want to talk about the other sort of half of the equation, the sine x equals negative 1, again, this is one of these cases where sine or cosine is 0 or negative 1 or 1. So the points on the unit circle are 1, 0, 0, 1, negative 1, 0. These are the quadrantal points, or the points that are on the axes. Which one of these represents a sine of negative 1? We'd have this one right here, the y value of negative 1, which means an angle of 270 degrees. All three of those will be our answer. Now, I think we should probably do this one graphically as well, because the way that we put it in the graphing calculator is going to be a little bit sort of sneaky. When I have this 2 sine squared x, here's how I'm going to have to put it in the calculator. I'll have to say 2 sine x all squared, because that's what sine squared x really means. Then I'll have plus sine x, and I'll have minus 1. Or I guess I could just do it from its original form, equals 1. Okay, so I could do the basic equation just as it's presented. If we got your GDC, graph, and you're good. So I put in my equation, 2 sine of x, close, close, all squared, plus sine x. I'm going to have equals 1 on the other side. I'm going to think about my window settings. My domain here was from 0 to 360, and I am in degree mode. My y's, I can go from -1 to +1. Maybe I'll go a little further, because I'm not really sure what the graph of 2 sine squared x plus sine x looks like. Maybe I'll just go from -5 to +5. As long as I see 1, I'm probably okay. So I hit graph, and I'm going to get an answer at about, I can just estimate these. You can see the x value in black at the bottom, at about 30 degrees, at about 150 degrees, and then a last one over here at about 270 degrees. Sometimes the graphing calculator has a hard time finding these ones that are just touching or tangential. So you may need to use an analytic approach. Of course, we could use second calc intersect to find these exactly, but I think it's pretty clear here that the answers are 30, 150, and 270 degrees. So here's another one where we've got a quadratic, and it's from 0 to 2 pi. So this one's going to be in radians. So I'm going to think that is kind of like having a y squared plus a y. And if I want to solve that, then I would factor with a greatest common factor. That'll give me 2 elementary equations, either y plus 1 equals 0 or y equals 0. Okay. So if I had this equation, the answers would be 0 and -1. Here, I'm just going to do the same thing. I'm going to factor this. Cos squared x means cos x all squared. So if I factor out a cosine, I'll be left with cos x plus 1. And if you're not sure, you could multiply back in, and guess what? We'll be back where we started. That's how we know that we factored correctly, is if we multiply back in and things work out. That brings us elementary equations of cos x equals 0 and cos x plus 1 equals 0. And this we could write as cos x equals -1. Now both of these are values that are going to be on the axes, so I'm just going to think about my unit circle. Maybe I'll just draw it once. There's 1, 0, 0, 1, -1, 0, and 0, -1. So where do I have cosines of 0? Cosines are x values. I have them here and here. So this one right here would be pi over 2, or 90 degrees. This one over here, I mean, you might not know off the top of your head what it is in radians. You might think 270 degrees. Here's one way to do it. You could say it's 190 and another 90 and another 90. In other words, it's 1 pi over 2, 2 pi over 2s, 3 pi over 2s. Yay! And again, we have nothing weird happening with the domain, so we don't have to worry about using periodic repetitions or anything, or there's nothing weird happening with the period. Nothing's been changed to the x's, so we get to just go straight to our answers. If I'm wondering where cosine is -1, that is going to happen right here, okay, which would be at 180 degrees or pi. And those are our 3 solutions in this domain. Let's deal with one last one. So we've got 2 sine squared x equals 1. Again, I'll go off to the side and think, okay, what would that look like if it weren't triggy? It would be 2y squared equals 1. And if you really want to, you can factor this. But I think it doesn't make that much sense. If you have no other terms, like no sine term or no y term, typically what we do is just the square root principle. We divide by 2, and then we square root. And when you square root in an equation, you need to consider that it's positive or negative, okay? Which would be plus or minus 1 over the square root of 2. And just so we're clear, 1 over root 2 is the same as root 2 over 2. I can prove it to you over here. If I took 1 over root 2 and I times it by root 2 over 2, which is just the number 1, I'd get root 2 over 2. Also, if I put it in the calculator, 1 over root 2 and root 2 over 2 would both give me about 0.7. So a bunch of ways to justify to yourself that those are the same value. We might want to write it that way just because we're used to it that way on the unit circle. Okay, so let's do the same thing over here. We're going to divide both sides by 2, so we get sine squared x equals a half. Okay. So if you're using square root principle, you don't need to make one side 0. I'll go through an alternate approach in a minute. We can square root both sides, so that'll be sine x is plus or minus the square root of 1 over 2. We've already established that that means plus or minus the square root of root 2 over 2. That is two different equations. Sine x is root 2 over 2, and sine x is negative root 2 over 2. Now, if you have other insights here or different ways that you'd like to do it, and that's probably okay as long as we end up with all 4 answers. So in both these cases, we're going to think about a reference angle. On the quarter circle, there'd be a point over here, root 2 over 2, root 2 over 2. Okay. And this tells us that's where sine is, and that would be a reference angle of pi over 4, or 45 degrees. Let me just make some space by getting rid of my quarter circle over here. Hopefully you have a quarter circle that you're using as you're working through these, and hopefully you can generate one easily. Either that, or you have another way that you organize your trig values. All right, now we're going to choose quadrants. Okay, it's going to be positive in these 2 quadrants. So we have an initial easy solution at pi over 4. We have another one at pi minus pi over 4, and so that's going to be 3 pi over 4. And you can take time off to the side if you need to do that. That pi over 4, or pi minus pi over 4, is like 4 pi over 4 minus 1 pi over 4. Hey yo, that's how we get our 3 pi over 4. The other equation also has solutions. So it's going to have the same reference angle, because we're still talking about root 2 over 2. But it would be in these quadrants. Okay, so I'm going to draw the solutions. Again, no funny business with domain happening, so I don't have to worry about periodic repetitions here. This first one's going to be pi plus pi over 4, which would be 5 pi over 4. And this last one is going to be 2 pi minus pi over 4 minus pi over 4, or 7 pi over 4. And here we go. So that gives us a way to solve these. For most of them, we're going to try and factor after making one side 0, and then we get 2 elementary equations to solve. They're both trig equations, so that's kind of painful, but it's not impossible. It's just kind of double the work. If you're really interested in factoring this one, I will show you how you could do that. You could write it like this, and then it would be a difference of squares. Now, if we think about difference of squares, if you had something like this, 4x squared, or 4y squared minus 1, you turn that into 2y plus 1, 2y minus 1. Things get a little dicier, though, if the first number is not a perfect square. So if we had 3 here, it's going to be harder to find the square root of 3, but not impossible. Sure, the square root of 3 is not an integer, but we can still write it. You can factor this as a difference of squares too. Okay, so 3y squared minus 1 would be root 3y plus 1, root 3y minus 1. I don't think this is the slickest way to do this problem, but if we wanted to factor this trig one, we could say, all right, well, it factors as root 2 sine x plus 1 and root 2 sine x minus 1. The nice thing about factoring is that you don't miss that second equation or that negative possibility. And we get this. And again, I don't think this is the slickest way to do this. And you could move stuff around. Equals -1, so sine x is negative 1 over root 2, which we know is negative root 2 over 2. Ha! That's one of the equations that we solved over here. And the other one's going to be root 2 sine x equals 1, or sine x over root 2, sine x is 1 over root 2, or root 2 over 2. And we'd still need to solve these. I'm not going to do it again because we just did it over here. So this is sort of option 2. I think if all you've got is a squared term, then probably do this square root principle like we did initially here. Okay, so in terms of practice, I've got some practice questions over here that I'll just put up on the screen. It's got stuff from this lesson and from the next one. So the ones that relate to this lesson are number 1, number 2, number 3, number 4, and number 8. Those are all possible. Number 8 has weird domain stuff or periodic stuff happening in it because it has a change in its period. Good luck with the material, folks, and take care.